Thanks for inviting me to this conference. And as always, it's nice to be back in Stony Brook, if only virtually. So thanks, Pradeep and Yair. Um, so I'm going to report some progress on a project that's been going on for many years in fits and starts. Uh, it's about trying to come up with an axiomatic theory of equilibrium selection that was started by Kohlberg and Mertens almost 40 years ago. So okay. So what we are after is a solution concept for finite normal form games. Okay. So think about these four axioms. The first one is just technical. Solution should be, what's a solution? A solution should be a connected set of Nash equilibrium. Okay. Closed and connected. I didn't put in closed there. It should be a closed and connected set of Nash equilibria. The other three axioms are more decision theoretic. Admissibility says that equilibrium solution should be in undominated strategies. The third property is backward induction. Okay. Every solution, which is a set of equilibria, should contain a backward induction solution, equilibrium. And the fourth one is what Mertens called small worlds, but actually Bob and I use it in a much more expansive sense. I'll define what that means later, but essentially it says that if we have a game that's being played by, say, two players, and we embed this in a larger game, what I would call a meta game, then the solution to this smaller game is unaffected by the fact that we embedded this in this larger game. Okay, so take these four axioms, and what Bob and I showed in a paper from years ago is that any solution concept that satisfies these properties on the domain of all finite games. So the axioms are imposed on all games, and we look at its implications for two-player games that are specified as extensive form games with generic payoffs. Okay. Then for those games, you must be selecting from stable sets. Okay, stable sets as defined by Mertens, as reformulated by Mertens. Okay, so that's what we did. So that was for two-player games. So what I'm reporting on today is an extension to n-player games, but still for generic extensive form games. Okay, so we don't know what happens for a non-generic extensive form game. Okay, so these are really, really non-generic normal form games. A generic extensive form game is still non-generic in a normal form, but it has enough regularity that you can manipulate the regularity to say something. In general, we don't know. So what's different is now we need to add another axiom, which has a flavor of independence of irrelevant alternatives. So I'm just calling it an IIA type axiom. Okay, and really this axiom has to do with the addition of dominated strategies. So I'm thinking of dominated strategies as being irrelevant, and I'm going to impose that addition of certain types of dominated strategies shouldn't affect the solution. Okay, and there are going to be two flavors. Unlike the earlier paper, there are actually two flavors to this axiom. There's a very strong axiom and there's a more reasonable axiom, I would argue. Depending on which form of the axiom you take, you get two different axiomatization of two solution concepts. Okay? One of them axiomatizes what we would call components with non-zero index or essential equilibria. The other one axiomatizes stable sets. Okay? So that's basically the objective today, to present this axiom and then essentially state the theorem. I'm not going to prove anything, given that I don't have much time. Okay, so before I do that, I just want to say that this is an axiomatization that's somewhat different from what you know or what you think of when you think of axiomatization of, let's say, the Orman-Shapley value. There we have a domain of games, D, let's say D is your domain of games. The axioms are imposed on D, and then we get characterization of a solution concept for the domain D. So this is different in two different senses. The first one is that the axioms are imposed on a universal domain of all finite games. So if you want, I have a domain gamma, which is the domain of all games, and then I'm looking at a subdomain gamma zero, and I'm saying if the axioms are imposed on gamma, what does that mean for games in gamma zero, which is a strict subset of gamma. That's point one. And the second point is that it's not going to axiomatize a solution concept, because solutions here are not single valued concepts. So we don't associate to a game a particular solution, but we actually associate a collection of solutions. So it's a correspondence, not a function from games to solutions. And given that, all we can say is we can characterize maximal solution concepts, which is to say any solution concept that satisfies these axioms must be selecting from these solutions. And the maximal one, of course, is what I'm going to describe. Okay, so in those two senses, this approach is somewhat different from a typical axiomatization of solutions. Okay. Okay, so a brief notation. I don't expect you to remember any of this notation. You don't really, since I'm not doing any proofs, you don't really need to remember much of this, except that by a game, I mean a set of players, finite set of players, and a set of strategies, actually strategy profiles S, okay? Little n denotes a player. So S is the product of strategy sets, okay? Each strategy set is finite. And then we have a payoff function that assigns to each profile a vector of payoffs, one for each player. That's a game G. Okay, so I just sometimes refer to a game just as G because the set of players in strategy set is fixed. E of G is the set of Nash equilibria of G. And I'm looking at the set of all finite normal form games. That's gamma. So that's my universal domain. Ideally, I would like an axiomatization of solution concepts for gamma. I'm going to give you one for a subspace. So a solution concept assigns to each game a collection of solutions. So what's a solution? It's a closed and connected set of Nash equilibria. Okay, so I'm really building into my definition of a solution concept the notion of connectedness and closeness. Okay, I'll talk a little bit about closeness. It's kind of fairly obvious. Connectedness, I'll say a few words in a few minutes. Okay, so that's what a solution concept is. Of course, the solution concept that assigns to each game the set of all its Nash equilibria, that's one solution concept, right? But our objective is to refine this. And I'm going to focus on two solution concepts because my objective is to provide an axiomatization of both of these concepts. The first concept is what I would call essential components of equilibria. So if you take any finite game, each of those games has finitely many connected components of equilibria. So maximal connected sets of equilibria. Okay, they're called components. And using fixed point theory, you can assign an index to each component, which is sort of a measure of robustness. So an index is an integer. And if the integer is non-zero, it means it's robust to payoff perturbations. Specifically, let's say the index is 3. One way to think about this is that if I perturb the game arbitrarily in an arbitrarily small way, then essentially there'll be 3 equilibria close by, accounting for signs of indices, because +1 and -1 have different properties. Okay, so it could be there are 5 equilibria, 3, it could be there are, okay, I got my counting wrong. So it could be there are 7 equilibria. Okay, so some of them are +1 and some of them are -1, and you sum them together, you get 3, for instance. Okay. Okay, so that's essential components. So non-zero index has a very vital role in fixed point theory. Okay. And that's one definition. Kohlberg and Mertens actually have a definition that's not based on index theory, but that's just a straightforward robustness criterion, which is that you have a solution if it's robust to all payoff perturbations. Okay, that's a slightly weaker concept. There is a small gap between these two concepts, but anyway. So, and then the other one is stability as reformulated by Mertens. And this is also a robustness notion, but here the robustness with respect to trembles a la Zelton. So players intend to play a strategy, but there's a small probability they play something else. And you want your solutions to be robust to all such trembles. Okay. So both of them, I explained them in terms of robustness, which you can think of in epsilon delta terms, but really these are stronger properties coming from algebraic topology. And the main difference is the domain of perturbations. One is based on strategy perturbations. The other is based on payoff perturbations. So strategy perturbations can be viewed as a special class of payoff perturbations. So one way to think of strategy perturbations is to say, I restrict the set of strategies you choose from. Another way to think of it is I redefine the payoffs at the pure strategies so it resembles a strategy perturbation. Okay, so two different ways. So payoff perturbation is more general. So those are the two concepts I'm after. Okay, they both involve concepts from algebraic topology, and that's what's going to give me leverage in combination with the axioms to say that this is what we should be going for. Okay, so let's talk about the axioms now. Again, the axioms are for the domain of all finite games. Okay, so in some sense, what I have, the first bullet point is axiom zero. It's really, as I said, it's built into the definition of a solution that solutions be connected sets of equilibrium. Okay, so to think about this in practical terms, if I think in terms of an extensive form game, and in fact, this is true for components of equilibria too. There are only finitely many equilibrium outcomes in a generic extensive form game. And each, by an outcome, I just mean a probability distribution over the terminal nodes. Okay, so there are only finitely many outcomes for each game. So you can think of the theory as trying to select an outcome. Okay, and connectedness allows us to do that. Okay, the other thing is it's in some sense a stand-in for a minimality condition, which you don't want to impose. So we want to try to keep solutions minimal, and actually this allows us to do that. Certainly for one of the two theorems, I can replace connectedness with minimality. Okay, just say solutions should be minimal, and the whole thing will go through. This is minimality of each solution. Remember that I'm characterizing in some sense maximal solution concepts, which is picking up as many solutions as possible. Here I'm talking about each solution being minimal, as small as possible. And the reason is that each solution is a set of equilibria. Ideally, you want to get a singleton. If that's not possible, try to make it as small as possible. Okay, so axiom A says that every solution should be in undominated strategies. Okay, so actually this was for two-player games. In n-player games, we would strengthen this to saying that all equilibria should be perfect equilibria, which you can think of as a generalization or a stronger version of requiring undominated strategies. Okay. So I'm not, given the lack of time, I'm not being more specific than that, but just think in terms of undominated strategies. Okay, axiom B, it's not the most ideal formulation of the axiom as far as we are concerned, but it's what we have right now. Backward induction should ideally be captured by sequential equilibrium. Krebs-Wilson notion of sequential equilibrium, but we're unable to make that work as an axiom. So we are using something that's slightly stronger called quasi-perfection, which is a concept due to Van Dam. it combines sequential rationality, in fact, with some conditional admissibility. That basically says if you're at an information set, your behavior from then on is also undominated. Okay. Rough, easier to think of it that way. Okay, so those are the two axioms about admissibility and backward induction. Now let me talk about the small worlds axiom, which is the third axiom that featured in our earlier paper. Okay, so if we embed the game in a meta game, okay, so I'm going to call the players, say Alice and Bob are playing a game, I call them insiders, and there are other players, I'm going to call them outsiders. Okay, they're not dummy players in the sense of not having any strategies or having payoff irrelevant actions. They're dummy players vis-a-vis the insiders, and I have a formal definition in a minute. If that's the case, then the solution of the original game should be solutions of the larger game. Okay, small worlds is a term that comes from Savage's theory of decision theory. Okay, so that's where the term comes from. So here is the formal definition. Okay, suppose I have two games, G and G tilde. Okay. And the tilde, sigma n is the set of mixed strategies in G, and sigma tilde is the mixed strategy in G tilde. And likewise, G tilde are the payoff functions. G tilde is a bigger game. It embeds the original game if the players in G are also players in G tilde. And I have these functions. You see, I have these functions here. Fn, n is a player in G. And I have a function for him which maps his strategy in the meta game and the strategy of the outsiders in the meta game to his strategies in the original game. Okay. It doesn't depend on the other players. So Fn does not depend on the strategies of the other insiders. It depends on his strategies and the strategies of the other outsiders. And that's a multilinear function which preserves payoffs. Okay, so that's the formal definition here. That's what it means to embed a game. Okay, heuristically, that's a lot to process with all the notation, but in words, this is what it's saying. Every player has a set of pure strategies that are equivalent to his original things. Okay, there are some strategies that are whose meaning and interpretation is unaffected by the outsiders. There are some other strategies whose exact meaning depends on what the outsiders do, but not in a way that distorts the game. So in particular, this doesn't introduce any correlation. It's very easy to see that the Nash equilibria of the original game are the projections of the Nash equilibria of the larger game. So I'm not introducing any correlation, nothing. Okay. Simply put, the outsiders' actions can be used as randomization devices for the insiders. That's what's happening. So what's the axiom? The axiom says if I embed the game in a larger game, then the solutions of the game are just the projections of the solutions of the larger game. The projections here are via these maps F. F is a map that allows you, it's like a dictionary. It tells you what the meaning of your strategy, whatever you do in the original, in the bigger game, it tells you what it means in the original game. Okay, so this is the theorem for two-player games. This is the old theorem. So suppose you have a solution concept that satisfies these axioms, A, B, and S, admissibility, backward induction, and small worlds. Then on the space of generic two-player games, it selects from among the stable sets. Okay. Now, for those of you who know the definition of stability, that definition involves looking at the graph of equilibria of overperturbed games and saying that graph has a projection that's essential in an algebraic topological sense. What basically what we're doing here is really converting this into converting that requirement into a fixed point problem. Okay, so it basically says asking for that kind of essentiality, that kinds of robustness is equivalent to solving all kinds of fixed point problems. And the combination of B and S really amounts to a fixed point problem. So B and S allows you to state a canonical fixed point problem, basically, that you have to solve. They give you the canonical set of fixed point problems that you need to solve, basically, because they all have to come from game theory. And this gives you the entire set of problems you could potentially be interested in. Okay, so that's what this is. So that's the theorem. In fact, this theorem crucially depends on having two players. So to give you an idea, even if I take, everybody knows the beer-quiche game. The beer-quiche game is thought of as a sender-receiver game. Think of it as a two-player game, but one could also think of it as a three-player game where the two senders are two different players. Okay. If I treat it as a three-player game, these techniques don't work to say that you must select from the stable sets. None of what we did none of what we did to prove this theorem works, even to solve that game. Okay. So that's part of the reason we were paralyzed. We didn't know how to proceed. So one needed a completely different axiom in order to be able to, so one needed more axioms in particular. Okay. So I'm going to just present this axiom now. So essentially, this last 6 minutes is the talk, is the subject of the talk. Okay, everything else was what we did in the past. Okay, so unfortunately, that's the best I could do. Okay, so this is the crucial axiom I want to talk about. It talks about dominated strategies. Okay, so Kohlberg and Mertens have a beautiful argument in the paper about deletion of dominated strategies, and so if you delete dominated strategies, then somehow the solution of the two games should be related. But they also have an argument that says that it may not be that reasonable to go the other way. In other words, this is not symmetric, that if you add strategies, somehow these two games are different, and they attribute an argument, I think, to Francois Fauche. But sometimes I think, we think that the converse is also reasonable. By the way, the same point was made by another student of Mertens, Federico De Gregis. He makes the same point in another paper of his, that we should think about dominated strategies more seriously. So, really, I should attribute this to him. Okay. So, this argument I should attribute to him. And I think it's also present maybe a little bit in Mertens's paper as well. So maybe I should attribute it to Mertens. So, so this is not terribly original. This is already there in the literature. Okay. So think about this game here. I've added, think about adding the bottom row as a strategy. Okay. This is dominated. This bottom row, if I've got it right, is dominated by by a combination of the other two rows. But from player two's perspective, it really matters. It doesn't matter, right? So if his choice between left or right is completely unaffected by whether this bottom row is there or not. Okay. So this is a kind of strategy that I should be allowed to add and insist that the solution not change. Okay. So I'm going for something like that. But to begin with, I'm going for something even stronger than that. And I say, well, what if we insist that adding dominated strategies should not change solutions? Well, let's look at that axiom. So we say that again, remember, this is the set of players, this is the set of actions, and this is the payoff function. So the bar game with the same strategy, player set as the one without the bar, is obtained by addition of dominated strategies. It's exactly what you would think. These strategies in S bar that are not in S are completely dominated, strictly dominated. Okay, so I don't want to get into a discussion of weakly dominated strategies or not. These other strategies are strictly dominated. And my axiom D star says a solution should be invariant under the addition of dominated strategies. This is a very strong axiom. It says nothing about the payoffs of the other players. If I have a dominated strategy and I add it, nothing should change. I'm not saying this is a reasonable axiom. I just want to know what happens if I look at this axiom. It's somewhat more reasonable is to impose some conditions on the payoffs of other players, when I add a dominated strategy like the bottom row, I could insist on some regularity in the payoff structures of the other players. And that comes in this next definition. Okay. Unfortunately, there's a lot of notation for you to read in 2 minutes. Basically, it says, when I play a dominated strategy, its payoff implications for you are as if they come from other strategies. Okay. And my strategy, what it means to me, is not distorted by any undominated strategy of yours. Okay. This imposes a little bit more restriction on.
Can you say that again?
Yeah. So when okay. So there is a way to map Doug, I may go over 1 minute. Okay. So there's a way to map. Sigma bar is a bigger game with dominated strategies. Okay. So I have a multilinear function from sigma bar to sigma. It's a way of mapping strategies in the bigger game to the original game.
Yes.
So if you take 2 different players and 2 different strategies that are in their original game, any undominated strategy of yours will not affect how my strategy is viewed in the original game.
I got
If I'm
you.
playing an undominated strategy. And 2 undominated strategies for me are affected the same way if you play a dominated strategy.
Mm-hmm.
Okay. This, by the way, introduces some correlation in the way things are brought in, but not in a way to distort equilibria or anything like that. So axiom D star is any undominated strategy should be fine. Axiom D is these kinds of undominated strategy are fine. This, for instance, preserves perfect equilibria, undominated equilibria, and so on. So I have 2 theorems. The first theorem is if you take the stronger axiom D star, any undominated strategy is fine. You characterize essential components for generic extensive form games. If you take the weaker axiom, you characterize stable outcomes. So the question of whether you think about payoff perturbations or strategy perturbations depends on which of the 2 formulations of these axiom is reasonable. And the other thing I have to say is axiom A, admissibility, is missing in the first theorem because connected sets violate axiom A. In other words, one could argue that you cannot insist on undominated strategies if at the same time you want invariance to addition of dominated strategies. It sounds a bit paradoxical, but A conflicts with D star, so you have to drop A. So that's all I have.
Wonderful. Thank you, Harry. Just on time. Any immediate or urgent questions or comment from the audience? We actually had a quite lively discussion in the chat that you may find useful just reading over Harry and Bob, but
okay, I'm sorry, I didn't
no, of course not. I was just amazed that there was actually, I think Yehuda was particularly helpful in clarifying and addressing
John,
some of the questions. So he must know your work very well, which is wonderful.
Thanks.
I get by these axioms, you then end by saying we select from the stable set. So in some sense, this would suggest that it's a subset that you're identifying with these axioms, or have you, I mean...
No. If you take these axioms and you take any solution concept
yep,
that satisfies these axioms, anything that it calls a solution has to be stable.
I see.
I didn't say the other part, which is that stable sets satisfy all these axioms.
Okay.
And another question, the results are in terms of stable outcomes and not stable sets.
Yeah, stable. I mean, I should have. Yeah, I was using it interchangeably here, but actually they are stable sets or potential components. Yeah, sorry. Thanks.
Excellent. Thank you.